Okay, I hope people can hear me online. Otherwise, you should shout out or something, but not during Kumar's talk. So it is my great pleasure to introduce Dr. Kumar Seluakumaran. Kumar is a senior lecturer at the University of Malaya, and he has a medical degree, and he arrived in 2002, we just established, in Australia to do originally a master's research program with Don Robertson, and I was happy to be his co-supervisor. And then he did so well that we changed that into a PhD. And so he graduated with a PhD in 2007. So he was the very first PhD student that I could write on my CV, so I have good memories. He was also a very good student, that's also very nice, so I wasn't traumatized from the beginning. And he also, his research actually kickstarted the tinnitus program in our laboratory. So his research was actually the start of the tinnitus work we did. He then went back to Malaysia, where he works in the physiology department, and he's a teaching and research academic. So he teaches physiology to medicine, biomedicine, dentistry students, etc. And then he runs a auditory laboratory in Malaysia. He's very much interested in how the brain processes sound and how this is affected in hearing loss. And he's also interested in the... What? Are you there? Trying to tell me something? No. And he's interested in developing inexpensive tests for hearing. I was very fortunate that a year ago or so he approached me to ask if I wanted to be a collaborator on a small grant. And we obtained that grant from which we now pay a PhD student who has just started. So I'm very happy to collaborate again with Kumar. And I'm also very happy that when he came over here that he offered to give a talk to our department. I should also say that while he did his PhD, he also managed to find a wife and get married. So he was very productive while in Australia, I must say. So it is my great pleasure to introduce Kumar, who will talk to us about earphones and hearing loss, and I will leave it up to him to explain it further. Thanks, Kumar.
Thank you. So thank you very much for being here, and I'm glad that I'm back at UWA, and also to meet all of you, especially my former supervisors. A lot of good memories back in UWA. So today's talk, I will address three important areas that I've divided here. So first 15 minutes or so, I'll introduce about earphone usage habits and potential hearing risk that it poses. The second part of the talk, I'll introduce on the pattern of hearing damage expected in regular earphone users. And in the third part of my lecture, or rather seminar, I'll talk about the options for affordable hearing tests that's available for screening purposes. So in the market, we have different types of earphones, and you all will be familiar with these types. Some of them go on the ear, around the ear, some of them inserted into the ear canal, or just outside the canal. All these earphones actually can produce high quality digital music, very loud level with minimal distortion. And typically they have diaphragms, so which when you apply a voltage, these diaphragms move in and out, and compress the column of the air adjacent to it, and that's how you get sound variation, sound pressure. And these sound waves travel through air and reaches the eardrum, and after which it stimulates the receptors inside your inner ear, and that's how the brain interprets the sound. Of course, you also have bone conductors or bone conduction earphones. These earphones are placed on the temporal bone because the inner ear is encased within this bone. The sound vibration actually travels directly into the cochlea or the inner ear and stimulates the receptor cells there, bypassing the outer and middle ear. So, irrespective of different types of earphones, the issue or the risk of to hearing damage is because of the sound exposure that comes out of these earphones. So traditionally, the damage related to sound exposure is also known as noise-induced hearing damage. The term noise is used here because historically this type of damages are seen in among factory workers or miners, where you have noise from machinery that damages the ear. So the main aspect, there are two main aspects to this exposure of sound. So one is the volume of the sound, which means the level of volume level setting that you use to listen. And typically, if you see all these social media advertisements, which tells you about safe listening, they always talk about safe listening volume. So this is a poster from NIH talking about music listening to music devices with having volume limiting controls, and so they emphasize on the listening volume. But on top of the volume, I will later show you some data that we think that the duration of exposure is probably a more important aspect of damage to hearing. And you have this not only the frequency of listening, number of hours in a day, also the duration in terms of years of usage. So at the point where you start, age that you start, and so on, it's probably also more important than the actual volume itself. How loud is too loud? So as I mentioned to you, noise-induced hearing damage is historically an occupational problem. So all the safety limit you will see that exists today is, and the data relevant to noise-induced hearing loss is based on data that was collected in 1960s from factory workers and miners in North America. So these data usually, based on this data, they come up with a safety limit, which is in most countries now is 85 decibels. Decibel is a unit that you use to measure sound level. So 85 decibels for 8 hours a day. Why 8 hours? Because that's the number of hours, working hours in a day, typically. So if you look at the 85 limit itself, the volume of a maximum volume of an iPod, for example, would reach definitely much higher than that safety limit. So this is, of course, without a safety limit that's imposed on these devices nowadays. This is a volume without that cap. Nowadays, people use smartphones, right? So I've actually gone back. So before I come to that, so I've actually recorded the output from smartphones, which I'll show in a short while, that they can actually come close to 100 dB as well. So they are equivalent to probably rock concerts and chainsaws when they are at max volume. Now, when we talk about volume or listening level, typically we measure the noise in free field, because that's an exposure in occupational setting. So you have this noise coming out in the environment, ambient noise coming up into the ear. So we typically use the point at B, which is outside the ear. But when you're using earphones, you're actually producing sound into the ear canal, and the measurement of the output of the earphones are usually at this reference point, closer to the eardrum. And as you can see from the transfer function, or rather the conversion from B to A, you'll see that at point A, some of these sound frequencies, certain sound frequencies are amplified by the outer ear and the middle ear. So the volume that you measure from the earphones are typically corrected to free field, so using an inverse function. So you have these free field equivalent levels. So it's important to remember whenever you see a volume, listening volume reported anywhere, it should be in free field equivalent level to compare with the damage risk criteria. So WHO in 2019 came up with a criteria for earphone listeners, so a safety limit for this type of exposure. So since the exposure starts very young age, they think that a safety limit should be much lower, slightly lower than the occupational setting. So the if a child is below 12 years old, then the safety limit would be acceptable safety limit would be about 75 decibels. And if it's more than 12 years old, then we can accept 80 decibels. Remember, these levels are free field equivalent levels. And in terms of safe listening duration, you can convert the 8 hours of 5 working days in a week into 40 hours a week. This is practical because you're not going to just listen to earphones during the working hour, but even weekends. So it's just to convert it into a per week basis. If you have volume levels above the safety limit, so you have a 3 dB exchange ratio where for each 3 dB increase in the volume, you actually halve the safe listening duration. So if you're talking about 100 dB, which is about here at the max volume, some of these headsets that you use, that within minutes you will reach the safety limit. I'm sure you've come across the 60-60 rule. Again, a lot of these social media, you have these posters coming out, safe listening, advertisements from different types of companies that talk about how you can use these earphones at 60% of the volume setting of the device for 60 minutes a day. So this rule actually was suggested by Fliger. Fliger is someone who works at Harvard. He measured the output from CD players in 2004 when smartphones were not around at that time. And based on his recommendation, the 60-60 rule is applied. So what I did was I took different brands of Android phones and tried to measure the output level and see if this rule actually applies to these phones as well. So here you see the free field equivalent output levels, and down here is the percentage of maximum volume. So one thing is clear that as you increase the volume setting of your device, the smartphones, you have a linear increase in sound level in dB. Remember, decibel is in log scale. And so I've used Android phones because 90% of the users in Malaysia, they use Androids. And these are coupled to stock earphones, and they are playing a standard music. Okay? So the variation, there's also some variation here from brand to brand. So this variation is because of the phone's audio chipset, as well as the sensitivity of the earphone that you couple the phone with. So if you look at a 60% volume setting, so the output ranges from about 80 to 90 dB. And if you look at this recommendation from WHO, they are from this practically correct level, correct range. So and if you take a mean or a middle level of 85, that would be 7 hours a week. So it's 60 minutes a day, right? So it's appropriate, I think, 60-60. But if you don't want to be too conservative, you can stretch it maybe to 90 minutes a day, especially if your output is slightly lower, in the lower range. Now I'll show you some of the data that we have collected from our population. So this is my one of my first PhD students back in 2013. We went to high schools around our university, collected their data about their listening habits, actually measured the output from their MP3 players. So you have a normal distribution, which mean about 60 dB. So these levels are actually 8-hour equivalent levels. So to compare the damage of this exposure to occupational setting, we've converted this using a formula. So you put in the average listening duration in a day and the free field corrected listening levels from the earphone, and you can calculate the equivalent levels. So as I mentioned to you earlier, 80 dB would be a safe listening duration based on the recommendation of WHO. So we would roughly get about 8% or 10% of the students exposing themselves to high risk behavior. But remember that data was collected in 2013, where majority of the users were actually using MP3 players, not smartphones. And pandemic was not around that time, so there was no online classes. So this was just based on the earlier data. So yeah, we also did another study on the university students as well. So they both gave roughly about the same, about 8% risk. This is our papers have been reviewed by others, together with the data from other countries. So you can see the mean here, pool estimate is about 25% risk prevalence, and but more recent studies would suggest that it's crossing closer to 50%, which means 50% of those aged between 18 to 35 are exposed to levels which can damage the hearing. So that's a bit worrying, because 50% is a large number, practically half of the generation. And so this is again emphasized in the recent WHO world report on hearing. And if I'm collecting the same data today from the same high school students, you would see a shift of this graph crossing over to this side. Now, if you take a mean level, so it's, let's say, closer to 80, and if you compare to other type of exposure from recreational sources, for example, concerts, music concert, or even gunfire, so they seem to be pretty safe, much lower than those other behavior or other exposure. But what is worrying is this part here, where you have this portion, a certain percentage of users using these devices at levels equivalent to more high-risk exposure. So one thing that we have also learned, that these particular users actually are those who are listening to in a very noisy environment. So particularly when they're traveling in a train or exposed in a road traffic noise, what happens is this type of ambient noise starts to mask the music that it comes out from the earphone, and therefore the user needs to crank it up and increase the music level to overcome the masking. And they tend to have much higher risk. And that's where you have newer technologies now, like the noise cancellation technology. So you have certain earphones which can track the noise, ambient noise, using a microphone, and then produce an anti-phase noise which cancels out the ambient noise. So when you on the active noise cancellation circuit, and you practically cancel out this noise, and it becomes quiet, and therefore reduces the masking effect, so you reduce the volume. So obviously, downside is they are much more expensive, this type of earphones, especially the ones with good active noise cancellation circuitry. So alternative would be to use an insert phone with foam ear tips to prevent the ambient noise coming in. Right, so that's the first part. So the user listening habits and the risk. Next, I'll talk about the mechanism of hearing damage and the pattern of hearing damage that you see in regular users of earphone users. So for that, you need to know some basic physiology. So you have the sound wave that I've talked about earlier that comes through the ear canal, after which it goes to the middle ear and reaches the coil structure here, known as cochlea. Within this cochlea, there are special, very sensitive sensory cells. They are known as hair cells, and they are very vulnerable to damage, to damage from this high level of sound exposure. This is the sensory organ within the cochlea, and the two types of sensory cells that you see are the outer hair cells and the inner hair cells. The outer hair cells act like they have the motor protein, and they act to amplify the signal, so they help to increase the sensitivity of your hearing organ to sound. And the inner hair cells act as the primary receptor organ, which transduces your sound into electrical signals, which are then sent through the afferent nerve fibers into your brain, so that your brain can interpret the sound signal. So excessive sound exposure can lead to damage of these receptor cells. They're very sensitive, particularly the outer hair cells. And now, more recently, we also know that there's some damage to the nerve fibers as well. So, to understand the damage, we also need to look at the mechanism of the sound transduction in the cochlea. So here the cochlea is straightened out. And what happens is once you have the vibration taking place, there's a particular membrane known as the basilar membrane. This membrane goes through a vibration and peaks at different spatial locations along the base, along the cochlea. And the high frequency sound will produce maximum vibration at the more basal end, whereas the low frequency sound produces a vibration more at the apical end. So we can see this something like different notes in a piano. So you have the high pitched notes at basal area here, and the low pitch at the apical area. So the outer hair cell damage that you see from the noise exposure typically starts at the more basal area, which belongs to the high frequency area. So this is a data obtained from university students, and this was done in 2015. So at that time, you still can get a group of students who were not using earphones at all. And right now, I think almost every student have got exposure. And another benefit we had was that because of cultural differences, these students were not exposed to other type of recreational noise like concerts and elsewhere. So the pop noise, concerts and so on. So you have very clear single exposure to earphone users and non-users. So the main results we obtained was that shift in a very high frequency region above 8 kilohertz. So this corresponds to a very edge near the basal turn of the cochlea. And here, these are users who are exposed to more than 75 dB and for more than 4 years. And if you look at similar data here, so it's just more than 75 dB, but less than 4 years of exposure, you see a much less shift. So what we think is going on is you need several years before seeing this type of damage at a very basal turn of the cochlea. Now, just to let you know that these frequencies we're talking about is very high, and they are much higher than the normal speech frequencies that you encounter in day-to-day listening. Most of them were between 1 to 2 kilohertz. So this is really high frequency. This is a work by a different group from North America. So they have college students again. They measured the sensitivity. So similar to our study, they also found a change in their hearing threshold or the sensitivity or the softest sound level they can hear. And the shift is also similar, very high frequencies. So this is more than 5-year use versus less than 5 years. So as I told you, it requires, the duration of exposure is very important. The longer you're exposed to it, these effects starts to accumulate, and then it comes up as a shift in hearing sensitivity at a very high frequencies. Then this is also the same group of college students, but binned according to the environment that they listen to. Remember, I told you that listening in noisy environment means listening at a higher volume level, and you can see those the sensitivity of those group is elevated, and it extends to about 4 kilohertz as well. So this extends down to the other frequencies. I mentioned about the function of outer hair cells as having a motor protein and amplifying the signal, increasing the sensitivity of the hearing organ to sounds. While doing that, they also emit a very faint or low energy out of the cochlea to the outer ear, and these are known as the autoacoustic emissions. So we can actually use sensitive microphones and measure these emissions, which indirectly tells us the the function or the cochlear outer hair cells. So here we have taken the emissions from the listening earphone users, personal listening device users, versus controls, the non-users, and we can also see a drop in the amplitude of the outer acoustic emissions, indicating that there is subtle outer hair cell damage that's going on, even at the frequencies much lower than 8 kilohertz. Which did not show up in the change on the hearing sensitivity, which I showed earlier. This is different data collected by Lieberman. Lieberman is from Harvard Medical School, and he studied a group of college students. The high-risk students mainly were from music departments, so they were exposed to not only earphones, but also music from the ambient music. And the low risk was mostly students from other departments. And you can again see the early change occurring at a very high frequency. And he also recorded autoacoustic emissions. And although the drop was not significant, you see a drop in the amplitude. But what was interesting is he added additional data on another type of recording known as electrocochleography. In these recordings, you put an electrode very close to the eardrum, where you record the electrical activity of the auditory nerve while giving sounds. So very similar to EEG recording of the brain. So here you indicate the initial peak is reduced in the high-risk group, indicating there's some degeneration of auditory nerve fibers. So remember this, we have about 30 to 40,000 auditory fibers in each cochlea. So this is summed activity of entire auditory nerve. So we won't be able to point out which region or which frequency is affected. But at least we know some degeneration of auditory nerve fibers probably happening. So in terms of pattern of hearing loss, you can classify them into two. So as I mentioned earlier, you can have subclinical outer hair cell damage that affects the hearing sensitivity or the thresholds in quiet environment at very high frequencies, starting at a very high frequency. And you can have auditory nerve degeneration, a particular type of auditory nerve fiber, the low spontaneous nerve rate fibers are affected. These are based on studies in animal work, and there is now some indication that these eventually leads to, first starts off as synaptic lesion and then degeneration of these fibers. Since these fibers probably are useful in listening in noisy environment, you see that it mainly affects the hearing in noisy background. Like they might hear perfectly fine when it's quiet, when it's done in a hearing test, where you present sounds in quiet, perfectly fine, but they will have problem in listening in a noisy environment. And this term is used now as hidden hearing loss, where it's hidden. The term hidden here implies that it's, the typical standard hearing test will not be able to pick up these deficits. So so far, these types of lesions appear as though they are minimal, just mild, but the most important thing is that these sensory damage to sensory cells and afferents are permanent. They don't regenerate, right? So, and they are also silent, which means the users are not going to notice this for some time. They're gradual and accumulate over time. And the main problem comes when you're older. So you're exposed at an early age and you wait many, many years later before you actually see the problem. And this is because all our ear also undergoes an aging effect, just like any other organs. And exposure to sound at a very early age would make your cochlea more vulnerable to the aging effect. And so this is the sensitivity that I talk about, hearing sensitivity. The plot like this is also known as an audiogram. So you have the sensitivity at individual sound frequencies at a different age group. And this is for females and this is for males. So you can see as you grow older, right, there's a shift in the hearing sensitivity, which gets poorer as you age. And this shift takes place after about 30 years or so. When you're 30, it gets worse here. And the exposure to, let's say, earphones and any other type of noise when you're at a very early age would shift this curve downward much earlier. So the problem will probably arise when your hearing loss starts to appear at frequencies which matches your day-to-day listening frequencies, which are between 1 to 2 kilohertz when you're much older. So you will start noticing the problem then. Of course, we don't have the direct data from humans because this is very difficult. You've got to do a longitudinal study and follow up people for decades before you actually obtain the data. But in animal work, there's evidence for this from animal work. So obviously, yeah, it's difficult to tell and explain this to the newer generation because it's just like telling them, give up your worldly pleasures now to enjoy an afterlife reward. You're gonna see, these effects much later. It's not something that you listen today to the earphone and tomorrow you're gonna have hearing loss. So, but you need to come up with innovative ways to encourage them and come to a compromise that you can listen, but please follow this safety advice. So, I think 60% volume setting for 60 to 90 minutes a day would be acceptable for most teenagers, and encouraging them to take breaks in between and using volume limiters available in the devices, and then use appropriate earphones, especially if you're listening in a very noisy environment, you're traveling in a train, you better use earphones that can minimize the ambient noise effect, like the active noise cancelling headphones or the insert types with appropriate ear tips, which can block or passively block the ambient noise. Of course, at the community level, you need to also have educational programs, very good public health policy for safe listening to these devices. And more importantly, since it's silent in the beginning stage, we need to have proper a comprehensive screening program, especially for kids, to detect hearing loss at the initial stage. So the last part of my talk, I'll talk about methods that we can develop, affordable methods which can be used to screen the initial stages of hearing loss. So first, let me introduce how hearing is tested. So if you have any complaints and you go to an audiologist, they will perform a hearing test for you. So typically, you put on a headphone, and then they produce sounds of a certain frequency known as tones, and these subjects are asked to press buttons when you hear them, hear these signals. And this, we then present them at different levels, and you track the softest level that can hear. So these are known as thresholds at each frequency, and you can then plot them as an audiogram. And typically, these tests are done in soundproof booths because you want to minimize the ambient noise. So these tests are done in a very quiet environment. Now, the problem with standard hearing tests like that is, first, it's expensive. Two, it's not portable because you have huge booths. How are you going to transport this? And also it's labor intensive. You've got to have people testing all this regularly. Large number of students in the school or in the universities. So there are now a lot of effort going on trying to make these tests more affordable, more portable, and allowing people to self-test. And this is possible because we also have smartphones with us. So we can use smartphones to generate signals, audio signals, and then use consumer headphones to couple them, and then use that as a method to replace the typical audiometer or the standard way of testing for hearing. So the one example will be, this is Hearing X group. This is from the South African group. and they have these smartphones coupled with earphones where you can actually have apps installed. You also have various type of applications available in Google Play stores, right? I'll come to the problems later, but yeah, there is such things available, and it's possible to conduct the entire hearing test using these devices. In Australia, I think you have this app known as Sound Scouts, and this, they can download for free. They can use that to test. They also, this is like they have a game, where children can play the game and track their threshold. The main problem with this type of testing is the ambient noise. Remember, I told you that you need a soundproof booth to reduce the ambient noise during testing. So the second problem is the calibration of the devices, because when users download into their phones, each phone has their own chipset, different chipset can produce different sound level, and then the earphones are also different with different sensitivity. So the final output that comes out very different, can be different from different brands of devices. So what we have done is, one of my studies is actually to come up with the computer-based program. We use LabVIEW. This is to program audiometer. This is very similar to a physical audiometer, but you have this software that you can download upload into your computer, and instead of the audio chipsets that you use in the internal sound card, you can replace them with external USB sound card, better quality ones. And what it does is then you don't have to worry about output as long as you use a similar earphone. Another advantage of using external sound card is that better quality sound card. They reduce the noise floor, and therefore you can track the quiet threshold at a level where it's very similar to actual audiometer. And you can then couple it with, for example, here we have coupled with an insert earphone. This is a consumer earphone, and we then put an overlying ear muff. So ear muffs are available as hearing protection devices. They're available in the market. They're quite cheap. So good quality ear muffs you put on top of these insert earphones. They will reduce the ambient noise. So I've done some recordings to record how much noise is attenuated. So here, if you combine an consumer insert earphone with an ear muff, they can increase the attenuation of the noise, ambient noise, close to about 50 dB after 500 Hertz. That's equivalent of having a single wall sound booth. So obviously higher levels, what happens is sound actually bypasses, goes directly through your facial bone and reaches the ear. We also tried the active noise cancellation method, combine them with active noise cancellation, but they work best only at very low frequencies. Right, so here you have both QC25 headphone with the headset, the active noise cancellation on. So you can see the improvement in ambient noise is basically below 1 kHz. The other problem with the using consumer earphones for hearing testing is, the output of these earphones has to be also calibrated properly because they're not similar to what's available. So here, calibration, you need the normal threshold in a healthy young adult. So basically, these values are given in the ISO document for standard earphones that are used in the clinic. So if you use consumer earphones, these values can also differ. So you have to be very careful when you're using consumer earphones for hearing tests. They don't have similar normal thresholds as the earphones, primarily because the insertion depth is different. And this will depend on the ear tips that you use. So there's so many different types of ear tips in the market, the foam types, the silicone, and we also tried other types of ear tips that is available. And this is part of the problem. So an alternative to that, so far talking about testing in quiet. So an alternative to this is to do hearing tests in noise. So you produce a background noise, mask a signal, and then track the detection level of the signal in noise. And this type of testing is widely available now. So one of the apps known as WHO app, WHO app, is introduced by the WHO. So you can download this for free and do a hearing test. So they use what's known as digit in noise testing. So they present signals which are recorded spoken digits, and you hear 3 different digits, and you press these numbers to correspond to the digits that you hear. If you're correct, they move on. They have about 23 different sequence, and at the end they will give you whether you pass or fail based on the detection threshold. The good thing about this type of testing, when you use masking noise, is that you don't have to worry so much about calibration, because you're not, they are tracking the signal to noise ratio. So when your noise level is higher in a certain device, your masking will be also higher, and the threshold will be higher. So since you're tracking the signal to noise ratio and not an absolute threshold like in quiet, the calibration will not be a big issue. Second, since you're doing a masking noise, you don't have to necessarily have a very quiet environment for testing. So these two are very good points of this app. However, there are also limitations for this type of apps. They are not ear specific, primarily because this particular test, they use anti-phase noise for both ears. So you have to use inputs from both ears at the same time. They don't tell you which ear is affected. They don't give you frequency-specific information, which frequency is affected. They just tell you whether you have hearing loss, pass, fail, and you got to then follow up with the proper hearing test. So in my lab, we are actually looking for an alternative measure that would replace this type of hearing test. So you will still perform this test in masking noise, but in a different way where you will be able to gather ear-specific and frequency-specific information. So to understand this, this measure, this is known as a frequency selectivity measure, or FS. We need to also understand how the cochlear processes multiple frequencies of noise. So in a normal conversation, it's a complex sound. You have many different frequencies stimulating your hearing organ at the same time. Each of these signals will produce a peak of when vibrating the basilar membrane, a peak at different spatial region of the cochlea, as I mentioned earlier. So the ability of this cochlea is to separate these frequencies. So they act like a frequency analyzer, and they analyze and separate this so that your ear can then hear different frequencies of sound. And if you look at this peak of this vibration, right? So this is also known as tuning, of cochlear tuning of these in the basilar membrane. And this, again, is closely related to the outer hair cell function. So if you remember, earlier I spoke about how these receptor cells, the outer hair cells, they help to improve the sensitivity of the cochlea to sound. But on top of improving the sensitivity, this also preserves the sharp tuning of the vibration. So in other words, they actually help to increase the resolution of the cochlea to frequency, different frequencies. So in image processing, you have this pixelation. So similar to that, here you have the frequency information being distributed spatially along the basilar membrane. And you can then take, so this tuning looks something like this. So along the frequency region of the cochlea, you can have sharp tuning of each region of the cochlea to individual sound frequencies. If you take, for example, tuning at a high frequency area, this is an area we expect to have hearing loss when you're exposed to earphone, and a defect to the outer hair cell would present as broadening of the tuning, because it is not so sharp anymore. And this will also give us a chance to have an alternative way to describe the cochlear lesion. Rather than just looking at the sensitivity of the cochlea to sound, we might be able to use a resolution, frequency resolution measure to then indicate the damage to the cochlea. So on that basis, so we use a method known as the notch noise method. So just bear with me, it's a bit more technical. So in this method, what we do is present the tone, just like in a normal hearing test, but at the same time, you present a masker noise, which helps to mask the signal. And in a normal tuned cochlea, so this is sharply tuned, you see the X regions. These are the regions, or spectral region, a frequency region in the masker that helps to mask the signal. So these regions are labeled here, right? And we then present another tone with a notch. Here, the notch represents the energy level of the masker around the tone which is taken out. So because we take out this region from the noise, the threshold will drop, because you can hear easily because of less masking. So if you we can then adjust the width of the notch, and then we plot a graph, and you get a graph something like this, the graph A. So here the mask threshold, which is represented by the height of these tones, T1 and T2, is represented in this graph in these 2 points. So at the 0 notch, which is this one, so you have a higher mask threshold, and as you introduce a notch, you will drop the threshold below at T2. Right. So this, if you happen to have a cochlea with damage especially to the outer hair cells, then you expect a broadening of these tuning, which leaves with area where you have masking still present when the notch is introduced, a similar notch is introduced. So you have a more flattened curve. Right. So we can then take the difference between T1 and T2 and take that as a measure of hearing of our frequency resolution here. So you have in curve A, we have a better resolution. You have a larger difference between the two thresholds compared to, let's say, this curve B with a poorly tuned cochlea, and you have a smaller frequency resolution. Now, this method has been introduced for a very long time. It's in 1980s by Patterson from Cambridge. He worked on this, and more recently, we know that more work has been carried out to introduce or to understand how the resolution changes with noise exposure. So, for example, this is the data obtained from primates. Here, the monkey is exposed to intense sound centered at 2 kilohertz, right? And unlike the exposure from earphones, so these primates are exposed to very high level sound, so they need only one single exposure, and you can see the damage taking place at a high frequency, similar to what you would expect to see in a long-term frequent earphone user. So you have the poor resolution. So you see the tuning curves. So the tuning of the cochlea is poorer at the higher frequency region after the exposure to sound. Here you have the similar graph that I've shown earlier regarding the notch noise. So if you introduce a larger notch here, and the thresholds drop. So this is before the exposure, and after the exposure, you see that at the frequency region where you have poor tuning, the curves becomes more flatter. So we looked at this data, and then we thought, why not use this measure as an alternative way to track damage in the cochlea, particularly in noise-induced damage. So this work has been recently published. So here we have used the same setup. Remember I talked about the LabVIEW program installed in a computer using a sound card, and then putting them through the consumer earphones, using consumer earphones. And we then measured the frequency selectivity measure. We call it TFS here. And the blue crosses here represent data from normal hearing listeners. And the red crosses here represent data from hearing impaired listeners, particularly those who have damage to either the sensory cells or the afferent fibers. We won't be able to tell because we didn't do further details on them, but there's ongoing work to differentiate them. So, and on the right here, it's a graph similar. The blue dots here represent normal, and the red dots here represent the hearing impaired listeners. So here we track the change of the TQ. TQ represents quiet threshold. Thresholds in quiet, the test that you do in normal hearing tests, you track their quiet threshold, and we look at the change from the mean, normal mean, and versus the plot it against the change in the frequency selectivity. So what you can see here is that you would see that like this dotted line, the vertical line represents 20 dB hearing loss. So all those who have more than 20 dB tend to have a poorer hearing frequency selectivity. And if you do a regression analysis, a 10 dB hearing loss in sensitivity will amount to roughly about 5 dB change in the frequency selectivity measure. Now, why do these breakpoint dots are also found in this region? This is because we are plotting for individual test frequencies. So some of these subjects that we got, they only had high frequency hearing loss. So this data is from the region where they had hearing loss, and these were taken from regions where they were normal. So it also tells us that this measure is very frequency specific. So if you have hearing loss at high frequency, you also have poorer frequency resolution at high frequency region. This is another work that we have taken this measure and compared it against the digit triplet test, the digit noise test we're talking about, but we did it in a single year because we want year specific information, and also a questionnaire that's regularly used in Malaysia to screen for early hearing loss. So here, this frequency selectivity measure is taken at 4 kilohertz. This is a region where, where noise-induced damage usually is tracked in normal hearing test. And TQ, again, we measured their quiet threshold in 1 dB, and you can see that there's a nice correlation between the quiet threshold and the frequency selectivity measure. We can then use what's known as the ROC method, so to calculate the sensitivity and specificity of the test, and gives at the optimal cutoff point, you give roughly about 77% sensitivity and 86% specificity to detect 20 dB hearing loss. That's acceptable, and probably better than the current not digit in noise test, where if you do it without the antiphase noise. So I'll just briefly talk about the advantages of this test. So you can run it through consumer devices, affordable, accessible, don't require a very quiet environment because again, we are using masking. So the signals are much higher level than quiet. Calibration may not be necessary. Again, with this, we are actually working on this because since we are tracking the signal to noise ratio in, not an absolute threshold, so we may not need to worry about the calibration issue. They provide year-specific and frequency-specific hearing loss information. Okay. So finally, the ongoing studies in my lab. The first one, we're also looking at frequency selectivity changes in the hidden hearing loss subjects. So we have a PhD student, Farah, who's co-supervised with Helmi here, and Norman. Norman is also a graduate from the audiology course here, currently heading audiology department in a different university in Malaysia. So we are looking at the FS changes in these subjects. The other project that we have is developing a mobile app similar to what WHO has. So we have an app like a FS screener. So rather than screening for hearing sensitivity, you can use this app where public can screen for their frequency resolution. So Easter is a PhD student of mine, came from China, and his co-supervisor is a colleague of mine in the department, Ho, and we have a collaborator from the computer science department. It's helping us on. And I also work closely with the ENT department in our hospital. That's where we get access to patients. And and we have a lecturer also doing her PhD, Jaya. She's actually working on the effects of earphone, not on the cochlea, but the vestibular system, vestibular organ, because we also know that they are both linked closely to each other, and there are some indications to show that there's some early vestibular damage taking place among regular earphone users. And Prof. Jayanti is head of ENT department who I work with closely, so this is also her student. Finally, thank you so much, right? And these are a list of graduate students of mine whom I use their data. Some of the data I've showed you work was done by these students. I thank also the staff of the department. Thank you so much for bearing with me the last 15 years in the department. Then special thanks, I have Don here. Don is my supervisor, right? PhD supervisor when I was at UWA. And I also worked with him when I came here 5 years ago during my sabbatical. And Jeff is from psychology, UWA. He introduced me a lot of the LabVIEW codes that I use to develop the programs. Jeff is not here today. I spoke to him last week. So finally, Helmi. Helmi was my co-supervisor, as I told her, actually confirmed with her just now that I was her first PhD student, and that's like 20 years ago. Yeah. Thank you very much again for the school for arranging the talk. And if you have any questions, feel free to ask. Yeah, that's my researcher ID, so you can look up and reason work. If you need the papers, I can email you. Yeah, you just email me. I give you the papers. Thank you very much.
Thank you, Kumar.
Yeah.
That's a very old picture.
Yeah.
He
doesn't look any older, either.
I know, but we do.
Kind of weird.
But we do.
Yeah.
Are there any questions from the audience? Don? I also have a look at
Using the
online.
FS method, I'm
We
intrigued.
go there.
I'm intrigued that you can use the FS method to look at hidden hearing loss. Correct me if I'm wrong, but my understanding of hidden hearing loss in the purest sense is that it's a nerve fiber problem, not an outer hair cell problem. The outer hair cells might have been affected,
You
but
would
they
see the
recovered.
chat.
You've got this nerve fiber degeneration. Why would you expect any change in the frequency selection in those circumstances?
Yeah, to answer that question, there are some papers that looked at hidden hearing loss where there are subclinical outer hair cell losses as well, coexisting with the synaptic loss. So they could, some of these hidden hearing loss may also have coexisting outer hair cell problems, which are not shown in the normal hearing test. So there's also some of our data that showed that the FS change can occur even before the shift in the hearing threshold. So they're probably more sensitive to pick up outer hair cell loss, which are not seen in the program. So we're trying to see how many of these hidden hearing or so-called hearing loss actually have a coexisting outer hair cell.
But it's an outer hair cell problem that's not manifest as a threshold shift, is that right?
Yes, correct. Subclinical.
So it's a supra-threshold.
We're still working on it. We're not quite sure of the exact mechanism. There are several studies that come up with this theory that there could be two problems, not purely synaptic.
So by subclinical you mean, I'm not sure what, but
Basically, it's not shown as a
threshold
shift.
Do you mean then for a standard audiogram?
Yeah, standard.
Standard audiogram, so it might also be higher frequencies. Any other questions? I have a question about the duration, actually.
Okay.
So you know, that's notice we say 60, but what do they say then about how long a break do a person need? What is the main mechanism they think is causing the actual damage to the system?
Yeah.
Is it mechanical damage?
That's how I understand this, is that you have this continuous shift, there is a continuous stimulation. So there's this the continuous release of the neurotransmitters, and then eventually there's some kind of toxicity that builds up in the afferent nerve fibers. So if you give it a rest, possibly they can have like reuptake of these chemicals, cleaning them up from the synapses. So, and I think the recommendation is not very long, but 5-10 minutes break in between. But we don't really have any data, especially in relation to earphone exposure. How long an ideal break should be. And it's difficult to construct an experiment because you're going to have to expose someone to levels that will at least show some kind of shift.
Well, I'm definitely guilty of doing it wrong. So, are there any questions online? from people?